for our Newton's Third Law of Motion project by Juliet, My Unique, Juan, and Destiny.
Original process, Julia Carrillo. Lab environment. Labs had space for carts, pulleys, or force sensors to move freely, flat and smooth surfaces to reduce friction, space for objects to move, and collide safety. Lab equipment. Pendulums of different sizes, track or smooth tables, simple machines such as pulleys, wedges, balances, and irons for traction, used to show equilibrium and mutual action and reaction. Experimental procedures, setup of two objects facing each other using the track as a pendulum, measuring of forces or motion of both objects, observing each object pushes or pulls equally in the opposite direction.
Original lab environment. A workshop surrounded with pendulums, springs, pulleys, and levers. Original lab equipment consists of tables for rolling balls or carts to test collisions, strings, pulleys, and weights to study tension and reaction forces, cannon setups to show equal and opposite recoil forces. The original procedures: pull one bob to a set height and release to strike the other at rest. Observe post-collision swings. Repeat with both bobs. Release symmetrically. Qualitatively argue equal and opposite interaction forces during the short contact.
Original process, Juan Rodriguez. Lab environment. Simple setup with two carts on a smooth track to reduce friction. Lab equipment. Two low friction carts, force sensors, motion detectors, and a track. Experimental procedures. One cart was pushed towards another. Sensors measured equal and opposites force during a collision.
Original process. So for the lab environment, this experiment was conducted in a controlled physics lab environment with a smooth, low friction floor to reduce resistance. The workspace free of obstacles to promote the safety and allow for accurate observation of motion, lighting, and availability space for surveillance for clear, visual, reliable, and recording data collection. For the lab equipment, you need two spring scales, two skateboards, or a low friction carts, motion detectors, and protective equipment. For the experimental procedures, place both skateboards facing each other on a smooth flat surface while having one student stand or sit on each skateboard, connecting with spring scale between the two students, and one student gently pulls or pushes the scale while applying a measurable force.
Original difficulties. Initial hurdles. Pendulum and collision tests were hard to make them perfectly balanced, difficult to remove friction or air resistance from experiments. Safety issues. Use of heavy pendulums became dangerous. Colliding objects would break or even bounce unpredictably. Equipment issues. Early tools like the pendulums and scales were not precise, and lack of consistent measuring systems. Information processing. All data had to be observed and calculated by hand. Results of dependent on careful observation and reasoning. Mathematics and logical had to be explained, though it could be seen directly.
Original difficulties. Initial hurdles. The phrase action and reaction led to confusion about which force came first or whether they were simultaneously and symmetric. Safety issues. Experiments with colliding pendulums or heavy masses might pose risk of damage or injury. Heavy weights unsecured apparatus. If a collision experiment used a spring-loaded weight or impact device, the rebound or fragmentation could be dangerous. Equipment issues. External forces. Friction, air currents, and vibrations could mask or distort the mutual pair of forces. Pendulums lost energy to air drag, friction at the pivot, and imperfect elasticity of the collision surfaces. Information processing. In scenarios including gravity, contact forces, and collisions, students fail to identify which two forces form the action to reaction pair.
Original difficulties, Juan Rodriguez. Initial hurdles. Understanding how force acts in pairs and ensures sensors detected both directions accurately. Safety issues. Avoiding fingers near a moving cart and making sure the track was clear before each trial. Equipment issues. Force sensors sometimes needed recalibration and carts didn't always roll straight. Information process issues. Confusing data when force sensors gave opposite readings that need proper interpretation.
The original difficulties. So intentional hurdles at the beginning of the experiment, one of the main difficulties was ensuring that both people on the skateboard started from rest and maintained balance before applying any force. Equipment issues. During the setup, the spring scale calibration was an issue. Some scales did not return exactly to zero, which caused minor issues in force. Readings repeated use also slightly stretched the spring, alternating sensitive. Additionally, the skateboards had differing friction levels due to wheel wear, resulting in unequal motion. And the safety issue was a major priority since the experiment involved movement on skateboards to prevent falls. The activity was performed on a smooth surface away from walls of sharp objects. Both persons were closed-toed shoes and were advised to bend knees slightly for better balance. Information processing issue. Collecting and interpreting data presented several challenges. Force readings quickly as spring scales stretch and release, making a difficult to record exact numbers.
Sir Isaac Newton's goal was to explain why motion happens to create universal laws that describe all physical actions. Newton wanted to understand how forces caused motions and how objects interacted. The discovery was intentional. Newton carefully studied motion, collisions, and forces between objects. Who was expected to benefit? Scientists and engineers to understand mechanics and motion, as well as inventors and builders in order to design a safe and efficient machinery.
Original motivation. Rene Descartes' goal was intentional to formulate laws of motion in a mechanically grounded natural philosophy. His work paved the way for Newton's third law, but he did not phrase it as for every action there is an equal and opposite reaction. Descartes expected that his laws would provide a rigorous mathematical foundation for understanding physical phenomena, bringing clarity and certainty to natural philosophy. Descartes' laws was a great benefit to philosophers, science, and the theological and metaphysical order.
Differences to the modern advancements. Advanced tools such as computer-based force sensors, high-speed motion cameras, and air-track systems allow scientists and students to measure equal and opposite forces with extreme precision. The modern protection slash safety. Students and researchers. For the modern differences to the modern advancements. Advanced tools such as computer-based force sensors, high-speed motion cameras, and air-track systems allow scientists and students to measure equal and opposite forces with extreme precision. The modern protection slash safety. Students and researchers. Modern information gathering. Information gathering has evolved from manual observation to digital data collection. The modern information processing. Once the information is collected, data are processed using computerized and analyzed programs and AI-based systems. These systems can convert raw force and motion data into statistical graphs, averages, and predictive models, improving accuracy and reproducibility.
Modern benefits. Benefits to other fields were that physics and education deepens the understanding of motion. Computer science, much like AI models, can predict force reactions in virtual testing environments. Constructions, like improving earthquake-resistant structures by disturbing opposing forces. Technology spawned by it is rocket propulsion systems, airbag force sensors, and robotics, as well as parts of motion tracking.
Modern benefits. Modern benefits. Cross-disciplinary innovation. The law is fundamental to fields from biomechanics to vehicle design to robotics. Its research drives improvements in these areas. Other fields that benefit: automotive and vehicle dynamic, biomechanics slash sports science, studies of how humans or animals move, which is walking, running, or swimming, use action to reaction principles to optimize performance or prosthetics. Examples of technology spawned: balloon powered cars slash simple thrust devices. Example: a balloon car that expels air backwards and the car moves forward due to the reaction force. A useful demonstration and education device.
Modern benefits. Juan Rodriguez. Explain modern benefits of research. Research on Newton's third law has led to advances in understanding force interactions, improvement, engineering designs, and safety systems. Explain other fields that benefit from research. Aerospace, automotive, and robotic fields apply the law to design propulsion systems, brakes, and robotic movement mechanisms. Examples of technology spawned: rocket pro- rocket propulsion, jet engineers, and even swimming techniques rely on Newton's third law. Every action creates an equal and opposite reaction.
The modern benefits. The modern benefits of research. The principle that every action has an equal and opposite reaction that has produced major benefits across modern science and engineering. Other fields that benefit. They have other several fields like aerospace engineering, mechanical engineering, robotics, and biomechanics, civil engineering, and sports science. Examples of technology. So it's jet engines allowing aircraft to move, safety sensors, seatbelts, and airbags, force reaction for protection, in industrial robotics, balance of force and ensures precise and stable movements in manufacturing.
Future expectations. Develop advanced propulsion systems like efficient rocket engines. Enhances robotics and artificial intelligence like better balance and precision responding to forces. Revolutionized transportation safety, smart vehicles that react to crashes using real-time force data. Advancing in medical and biomechanical engineering, improving prosthetic limbs by responding to patients' motion and reaction forces. Potential benefits to come: cleaner space travel with low emission propulsions, advanced robotics and AI that interacts with humans more naturally. Better healthcare through adaptive prosthetics and rehabilitation technology. More sustainable energy production and enhanced learning and training with realistic virtual environments.
Future expectations. Future goals for scientists: design adaptive materials. Scientists aim to engineer systems where the action to reaction principle is used deliberately to generate motion, adaptation, or response. Potential benefits: better modeling and prediction, extending or challenging Newton's third law in non-reciprocal systems can lead to deeper insights in physics, uncovering new phenomena in non-equilibrium systems, active matter, and other frontier areas. Biomedicine and micro robots and soft robotics and cellular scale machines leveraging action to reaction at micro scales could lead to breakthroughs in targeted drug delivery, implantable devices, minimally invasive machines that navigate the body by pushing/pulling internal fluids or tissues.
Future expectations. Juan Rodriguez. Predict future goals for scientists. Scientists may use Newton's third law to improve sustainable propulsion systems such as ion thrusters for deep space travels or more efficient electric vehicles. Explain potential benefits to come: advancement in robotics, aerospace engineering, and renewable energy systems could energize from deeper applications of Newton's principle of third motion and reaction forces.
And for the future expectations, predict future goals for scientists. The future goals are to develop propulsion mechanics that uses plasma or ion reactions instead of using chemistries. It could more likely reduce more fuel emissions. Potential benefits to come. The benefits to come expectations surrounding Newton's third law of motion is to involvement applying principles to advanced technologies that can push boundaries of physics, space exploring, and energy efficiency.
Original motivation. Juan Rodriguez. Original goals of scientists. Isaac Newton aimed to understand how force causes motion and how objects interact when they push or pull on each other. Indicate if the discovery was initial. The discovery was initial. Newton used logic and observation to create mathematical law of motion. Indicate if the discovery was accidental. Not accidental. It was the result of deep study and systematic reasoning about force and motion. Describe who was expected to benefit. Scientists, engineers, and inventors benefited by applying Newton's law to machines, vehicles, and structures.
The original motivation. So John Willis' goals were intentionally not an accident. He was
Original benefits. The immediate benefit of Newton's third law was that it helped scientists understand how forces work. It also improved accuracy in motion, collisions, and balance. It gave clear explanations for why objects move or stay still. The immediate advances were in science and engineering. It led to better designs of the machines, tools, and vehicles, while also helped the early builds of rockets. The impact on other fields was that it influenced engineering, architecture, and transportation design.
Original benefits. Immediate benefits of discovery: The law of action and reaction ensures that internal forces cancel pairwise, so the total momentum remains constant. It helps explain everyday phenomena in a unified way, like jumping off the ground, rockets launching, recoil of guns. The law therefore gives theoretical justification for why momentum is conserved. Immediate advancements in its original field. It allowed physics education and engineering mechanics to be formalized in other fields, and biomechanics / human movement, walking, swimming, jumping, all rely on pushing something, ground or water, and receiving the opposite reaction force to move. In new fields, understanding action to reaction at new scales or with new materials enables innovations in metamaterials, active materials, and next generation propulsion. The law provides a benchmark, and deviations from it open new design spaces.
Original benefits. Juan Rodriguez. Explain the immediate benefits of discovery. Newton's third law of motion helped explain how forces interact between objects. This allowed better predictions of motion and balance in physics systems. Explaining immediate advancement. An original field. Revolutionized physics by unifying motion and forces under universal law. And brand new fields. Laid the groundwork for engineering, aerospace, and biochemicals.
Modern process. Environment well lit. The environment was a well lit lab and classroom with long and level surface tables, clear safety with no loose objects. The equipment, motion sensors, high speed cameras, computer software to record and plot forces, and electronic stopwatches. Experimental procedures, calibrating sensors and motion detectors before trials with attached sensors of objects can now be recorded during contact, being able to record data simultaneously with the sensors.
Modern process. Modern lab environment. A put together physics laboratory with a flat bench or dynamics table, ideally with air track or low friction track to minimize external forces such as friction. Modern lab equipment. Dynamics track and accessories. A low friction track, carts that roll with minimum friction, pulleys, strings, mass hangers, elastic bumpers. Computer with software to collect data from sensors, display force versus time graphics. Force versus time graphs, sorry. Compare force pairs, etc. Modern experimental procedures. Set up the apparatus, configure the data acquisition, perform the interaction, observe and record data, and then analyze and interpret.
Describe modern lab environment. Modern physics and engineering labs used high precision sensors, vacuum chambers, and digital simulations to study the effects of forces and motions predicted by Newton's third law. Describe modern equipment. Equipment includes force sensors, motion tracking cameras, air tracks to reduce friction, and computer interfaces to visual equal and opposite reaction forces in real time. Describe modern experimental process. Students and scientists often conduct controlled experiments using data acquisition software to measure how action and reaction forces act on different objects, verifying Newton's third law with modern accuracy.
The modern process. The modern process. Modern lab equipment that is needed: an air track and gliders, dual force sensors, data location systems, a computer motion detectors, and a protective gear, modern lab equipment. In a modern physics laboratory, Newton's third law of motion can be described in a digital, data-driven environment designed for precision and safety. The lab typically includes sensor-based systems, law fiction, attraction, computerized data software to minimize human error, modern experimental procedures, set up air track on stable surface, attach force sensors, connect both sensors.
Modern engineering understanding forces are now analyzed with computer simulations or accuracy in real-world conditions. Modern propulsion systems are optimized using digital modeling and sensors to measure the thrust and reaction precisely. Information gathering processing. High-speed cameras and digital sensors record how forces interact in experiments. Computers process large amounts of motion data, analyzing for allowing scientists visualize and refine models with such accuracy that then with zero technology Sir Isaac Newton had.
Modern differences. Describe modern protection/safety. Embedding privacy and protection features into systems from the ground up rather than as an afterthought. They help manage the tension between innovation, collecting, processing data, and privacy safety. Describe modern information processing. Big data and analytics, AI/machine learning processing, real time processing, and edge computing processing happens closer to the source of data, enables organizations to turn raw data into insights. Predictive modeling, automation, and better decision making faster. Describe modern information gathering. More data means better possibilities for insights, forecasting, automation, improved services, because gathering is so extensive. Frameworks and transparency efforts are emerging to ensure data collection is ethical, minimized, and considered.
Modern differences, Juan Rodriguez. Describe modern advancements. Modern physics and engineering uses Newton's third law and advanced simulation and computer models to design vehicle, robots, and aerospace systems with high precision. Describe modern protection/safety. Modern safety features such as airbags and crash testing systems rely on understanding reaction forces to protect passengers during impacts. Describe modern information gathering. High-speed sensors, cameras, and digital forces probes allow scientists to record reaction forces in real time, providing more accurate and extensive data than ever before. Describe modern information processing. Computers, algorithms, and AI analyze force data instantly, modeling reaction forces and optimizing mechanical system efficiently.
Modern